This is lesson 2, part 1 of lesson 2 in unit 4, applications of differentiation, which is straight line motion connecting position, velocity, and acceleration. Now this is a nice bridge between what we've been doing and what we're going to do with the rest of this unit with related rates. And that is seeing the connection between the derivative and rates of change, direction, how it affects the behavior of a particular situation. So what we have on the first page of the notes is vocabulary review of the different types of related rates, straight line motion concepts that we discussed, such as position, which tells you where the object is located, average displacement, which is position over time, or it could also be seen as the slope of the secant line. Then we have our instantaneous velocity, which is our derivative of our position function. Speed, which is the rate the position is changing, and of course that is always positive, so it is the absolute value of the velocity. Our acceleration, which is the second derivative of our position function, or the derivative of our velocity function. And I just want to make note here that we want to think about different ways we can write the derivative, because the Leibniz form of writing the derivative is going to become important when we're trying to find related rates. So you just want to keep that in mind. Displacement is, of course, the distance it traveled from start to finish. And then we have free fall motion with our gravitational constant. Remember that we can tell when the direction changes from positive or negative, when the velocity is 0. And also to remember that velocity and acceleration have to have the same sign if the particle is speeding up. They have opposite signs when it's slowing down, and if acceleration is 0 and velocity is not, the particle is moving at a constant rate. And of course, finishing out our review are the two gravitational constants, one in metric and one in our old-fashioned Newtonian units. I can't remember the official name of them. Okay, so what we're going to focus on in this lesson is to make connections between velocity and acceleration functions and as they relate to the skills on the AP exam. In fact, the last page of this section deals with calculator questions. So let's just hop right into these examples because they're just going to be a continuation of what we did in Unit 2. So example 1. A particle moves along the x-axis so that at any time t greater than or equal to 0, the position is given by the function x of t equals t to the third power minus 9/2 t squared minus 12t plus 5. So our first question asks us, at time equals 0, determine whether the particle is moving to the right or to the left and explain how you know. So we will know depending on the sign of the velocity. So we want to find the derivative first. So we're going to find x prime of t, and that's going to be our velocity of the particle. So when we do that, we get 3t squared minus 9t minus 12, and we want that value at 0. And when we do that, we get negative 12. Since this is negative, we can say the particle is moving to the left since v of 0 is less than 0. Okay, part B. At what time or times does the particle change directions? Justify your answer. So what we want to find is, when is v of t equal to 0? So we're going to set the derivative equal to 0 and solve. So when we factor, we get 3 times t minus 4 times t plus 1 equals 0. So our two zeros are t equals -1 and t equals 4. Obviously, t equals -1 is out since we can't have a negative time. So what we're going to do is at 4 seconds, and so we know before that time that the particle was moving to the left because our velocity was negative. So let's just look at the next second. Let's see what's happening at v of 5. And so when we do that, we get 3 times 5 squared minus 9 times 5 minus 12. You could have used 4.1, but I used 5. I guess I am a little far away. But what I see here is that my velocity at 5 is a positive number. This is greater than 0. So it has changed directions at 4, just to be on the safe side. So we can write the particle changes direction at 4 seconds from left to right. Because now the velocity is greater than 0. Okay, next part. At t equals 1, the velocity of the velocity of the particle increasing or decreasing? Explain your answer. Okay, so what we need to find out is what's going on with the acceleration. So does it have the same sign as the velocity, or does it have a different sign? So we need the acceleration. So a of t is going to be the derivative of the velocity function. And so our velocity function is right here. So we're going to take the derivative of that function, and we get 6t minus 9. So we want a of 1, which is v prime of 1, which is going to be 6 minus 9, which equals -3. Okay, if you recall, up to t equals 4, the velocity was negative. So we can write that. So from 0, there it is. Velocity was moving to the left. So v of t was less than 0. And now, so that means at v of 1 is less than 0 and a of 1 is less than 0. They have the same sign. So the velocity is increasing. All right, part D. At t equals 1, is the speed of the particle increasing or decreasing? Justify your answer. Okay, so let's find the velocity at 1. So v of 1 is going to equal 3 times 1 squared minus 9 times 1 minus 12, which equals -18. And a of 1 is going to be 6 minus 1. We already did this one. Minus 9, which is -3. And since they have the same sign, the speed is increasing. It's just another way. It's kind of the same as part C, but you just want to make sure you're distinguishing what kind of words they're using. In number 3, they were talking about velocity. Number 4, they're talking about the speed. Now, you don't want to get thrown by that because the idea of finding those two are the same. Obviously, if the velocity is increasing, the speed is increasing. It's not about the sign, it's about of the velocity, it's about whether or not the velocity and the acceleration have the same sign. So just be careful of that. That's why those two questions were put there. But even though they give you the same answer, they're talking about two different parts of straight line motion. Okay, finally, what is the particle's acceleration at t equals 1/4? Explain the meaning of your answer in terms of the particle's velocity. How would units be explained in context of the particle? Okay, so since we already have the acceleration, excuse me, we can find a of 1/4, which is going to be 6 times 1/4 minus 9. So this is going to give me 3/2 minus 18/2, which is going to give us negative 15/2. So the position's acceleration, the particle's acceleration at t equal to 1/4 seconds. I don't know where I'm getting seconds from. I think there's seconds in this. Let me just double check real quick. Does it say that? Doesn't say. I just somehow picked up seconds. Okay, seconds. So the particle's acceleration is negative 15/2. The velocity is increasing. Since v of 1/4 will be less than 0, and the units are distance. Sorry, I ran out of space here. Distance over time squared. Okay, and of course, it wouldn't be a section if we don't include a table. So example 2 is a table. So example 2 says, the table below gives the velocity in feet per second of a particle moving along a horizontal axis. The velocity v is a differentiable function of time t. So now we have time and velocity, and we are given units in this problem. So part A says, at time equals 0, determine whether the particle is moving to the left or the right. So what we want to see is that since v of 0, which is right here, is less than 0, the particle is moving to the left. Okay, part B. Is there any time or times during the interval in 15 seconds that's given when the particle is at rest? Explain your answer. So what you'll notice here is between 2 and 3 seconds, the velocity changes from negative to positive. So that's when the particle is going to be at rest. So we're going to say between 2 and 3 seconds. I don't know why I'm having a delay here in my writing. Since v of t is differentiable, which is given in the beginning, and therefore continuous. I hope you guys know where I'm going. So by the IVT, I knew you knew that was coming, v of 2 is less than 0, and v of 3 is greater than 0. Oh, that doesn't look anything like there. There there exists a t such that v of t equals 0. You always have to look for that. It's coming. If they're asking you to find someplace, some value, you're in between a range of values, you're talking about the IVT. So just don't lose sight of that as we go forward. Okay, part C. Use the data from the table to find an approximation for v prime of 8. Explain the meaning of v prime of 8 in terms of the particle's motion. Show the computations that lead to your answer and indicate the units of measure. Okay, so we're going to have to approximate a slope from what's given in the table. So v prime of t is going to be a difference quotient. Why should be 8 in there? I'm sorry. V prime of 8 is going to be approximately equal to, so let's look at our table and see what values we have. We're going to have to look between 7 and 10 here. Okay, so we're going to use v of 10 and v of 7, which are 5 and 3. So we're going to do v of 10 minus v of 7 over 10 minus 7. So this is equal to 5 minus 3 over 3. So our slope is approximately 2/3 feet per second squared. Okay? Explain the meaning. That's the only thing we haven't done. We've shown the units, we've shown our work. So we're going to say at t equals 8 seconds, the rate of change of the velocity or if you want to say the acceleration, you could say that too, is 2/3 feet per second squared. Okay, part D. Find the average acceleration of the particle in 10 to 12 seconds. Explain what this means in terms of the particle's velocity in the interval. So it's going to be the same idea. V prime of 8 is the same as the acceleration. So we're going to find the average acceleration, and this time we want not this range, but we're going to use this range here. So we're going to use these values. Okay, so the average velocity that we're looking for is going to equal v of 12 minus v of 10 over 12 minus 10. So we're going to have 3 minus 5 over 2, which is going to be -1. And so we're going to have -1 feet per second squared. So what does this mean? This means the average velocity, the average acceleration of the particle is negative so it is slowing down at a rate of -1 feet per second squared on average. We really should put that there because it's average. Okay, and then finally, let A of t be V prime of t. Is there a time t equals c guaranteed that A of c equals 0 in the interval 0 to t, where, t is between 0 and 15. Justify your answer. So there's some words here that should pop out at you, which is guaranteed, interval. That is the IVT. So we're going to go through this again. This is a different way that the IVT might be presented in a problem. So we're going to say yes with a Y, not a weird thingy. Okay, yes. Since V of t is differentiable, A of t equals V prime of t is continuous. I want to make sure the function you're talking about, in this case it's the acceleration, that you say it's continuous. A prime of 8 is approximately equal to 2/3 that we found above in part C, which is greater than 0. And A average velocity over the whole thing is equal to -1, which is less than 0. Then we can say, thus, A of t equals 0 is on, and actually, you know what, it'd probably be better here, instead of saying A average, that you could say that A prime, I'm sorry, A of, like, we did 7 to 10, so we can just say like A of 8. Oh no, I'm sorry, that wasn't 7 to 10. That was 10 to 12. So you could say A prime of 11, say something like that. All right, come on. A of 11 is approximately equal to -1. Thus A prime of t on this average, on this interval. Get rid of the equal to's. By the IVT. And I'm going to stop there, and we'll continue this in the next video.